Hey, you. Yes, you. Do you know linear algebra? Yes? Good. Then you are recruited. You see this? It's called an Enigma machine. Alright, basic training and history lesson. Here we go. Ever since there was a thing called strategy and tactics, it had become necessary to be secretive about one's words. Imagine today your group chat got leaked. Not a funny side in it. In 1918, a German engineer named Arthur Scherbius patented the Enigma machine. First off the shelf, it was sold to banks, railway, and trading companies, and other organizations who needed their messages encrypted. By the mid 20s, the German military started to use the Enigma machine, with some modifications to differ it from the commercial version. The Enigma was extensively used by the Germans throughout World War II. Therefore, breaking the Enigma cipher became a top priority, first by the Second Polish Republic, a great country by the way, then later by the British and Americans. In this video, we will only explain how the Enigma machine works based on simple linear algebra logic and some German ingenuity.
General mechanism. There are two keyboards in the Enigma machine. A normal keyboard you can press, and the LAN board. Corresponding to the name, the LAN board contains a series of the letters, still organized in the order of the keyboard, that lights up in response every time you press the normal keyboard. So, every time you press a letter on a normal keyboard, a letter on the LAN board will light up, but it will always be a different letter than the one that was pressed. So in the end, the sender types whatever they want to deliver using their normal keyboard, and the lighted up letter in the LAN board shows an encrypted version of the typed-in message. For instance, you type in hello, the LAN board correspondingly sends out AKGDY, that is your encrypted message. So technically, how does this machine work? The machine consists of three main parts. 1. The input wheel, connected to the normal keyboard. Simply, you press a button on the keyboard. This translates that press into the electricity signal which travels through the three rotors. 2. The rotors, responsible for the scrambling the letter. In other words, they do the encryption. There are three of them. Each time an electricity signal passes through a rotor, it modifies and passes the signal to the next rotors. The working mechanism of the scrambling stuff can be explained by the following. The letter A is input into the rotor 1, it becomes B. P goes into the rotor 2, it becomes B. B goes into the rotor 3, it becomes T. And the letter T is then put into the reflector. 3. Reflector. After being modified 3 times, the signal exactly reached the reflector. This part works exactly like how it was named. It modifies the signal one more time before continues passing the signal once again through the three rotors. 4th, the blockboard. Signal from the rotor 1 goes all the way to the blockboard, where the machine operator can then decide which letter to mix with which letter again. So the circuit of the encryption is as follows. Input wheel to the rotor 1, to the rotor 2, to the rotor 3, to the reflector, back to the rotor 3, to the rotor 2, to the rotor 1, to blockboard, and to the LAN board. The initial signal is scrambled for 7 times. You will notice that when we press double L, it comes out as GD. That is because for every letter pressed, the rotor 1 will turn 1 time, but after 26 turns of the rotor 1, the second rotor will turn once, and the same for the third rotor. So, there will be no repeated letter after it has been encrypted. So, how does all of this work in linear algebra?
We begin with a basic identity matrix, 26 by 26, so that we can map a letter to each position on the diagonal. This makes the alphabet a vector of dimension 26. For examples, we'll use 6 by 6 because it displays constraints, although the behavior translates to 26 dimensions. D is the keyboard input, E is the LAN board output, and A is the identity matrix representation of the keyboard with 26 letters. For demonstration, we will use only 6 letters. The rotors matrix in an Enigma machine is simply the identity matrix with swapped rows. After exiting the rotors matrix is transformed again at the pugboard, essentially the same function as the rotors. So if we consider the final result is the matrix A with swapped rows 1 and 3. Now instead of row 1 being A, it is C, and row 3 is now A. Example matrix B with swapped 1 to 3, 4 with 2, and 5 with 6. We call B the swapping matrix. Every time a letter was entered, the first rotor shifts 1 position. After 26 steps of the first rotor or full rotation, the second rotor moves 1 position, and so on. There were 3 rotors in place at a given time. This movement can be represented by a shifting matrix, which in this case is just the identity C. So after inputting any letter to the Enigma machine, the end result can be calculated by multiplying B to C. Now, if we input, for example, D into the machine, the LAN board returns a C. This B is multiplied by C matrix is called an output matrix. Now, how do we, the receiving end, solve this? A key aspect of swapping matrices is that when one is multiplied to itself, the identity matrix is obtained. That is, for some swapping matrix B, B squared equals I. Therefore, B equals B to the power of -1.
Imagine a linear function e ranges from R26 to R26. Another variable must be included in order to model the Enigma, the character index. We call it C. When a letter is pressed, it will go through the circuits of encryption we have shown before. Each of those stages could be a matrix. The blackboard matrix is a static swapping matrix because it doesn't move. We call it P. And for the alphabetical matrix, we call it A, and A ranges from A to Z. If we only consider the blackboard and the keyboard, E equals P times A. When a letter gets inputted into a rotor, it will get swapped with another letter. This scrambling function is called scrambling matrix C. A letter passes through the 3 rotors, so we have C1, C2, and C3. We know when rotor 1 moves 26 times, rotor 2 moves once, same for rotor 2 and 3. We call this a shift. We now have a shifting matrix X. Now, the E function should look like this. Note that the division will always be an integer, like C equals 3, then C over 26 is 3 over 26 equals 0, or C equals 26, then C over 26 is 26 over 26 equals 1. Also, the rotors may start at any setting, so we must include an offset F1, F2, and F3 for the 3 rotors respectively. All that remains to define E is the reflector, denoted by the matrix R. R is a swapping matrix. When the signal goes through the rotors a second time backwards, the wirings in the rotors are swapped from input to output and vice versa, so the matrices are all inverted. For convenience, let's name every C times S by the power of K as Q1, Q2, and Q3. From a diagram, it looks like the whole procedure produces a swapping matrix. T goes to G, and G also goes to T. That's the linear algebra for the Enigma machine. In reality, to solve the swapping matrix, the recipient of the message will receive the order on how to set up the rotors, the blackboard, and how many rotations rotor 1 needs to move in order to trigger the movement in rotor 2, in other words, the matrices. These orders change daily, so if the enemy got hold of one machine, if they don't know the order of that day, it's useless. To sum up, the Enigma machine was a very effective encryption tool for its time. but it was eventually cracked by the Allies through a combination of clever code breaking techniques and a lot of hard work. But that's the story for another day. Thank you for watching. Goodbye.